Hello everyone. I'm going to begin by hopefully, it's always hopefully when you do technology, zoom off to where? Zoom off to here. Right. So I'm going to click on this one. Are you looking at Math 146, our particular class, right? So I want to spend a little bit of time, since for some of you this is really the first time you may even have seen this. I hope by now that you've at least had a good look around Canvas. There are tons of stuff here. Anything to do with Zoom or things going wrong with Zoom, these are the links you can click and it will give you some videos on what you can do to maybe fix it. If you need some tutoring, there's your link, you can go. You've paid for it anyway when you pay for the class, it's not going to cost you anything. Otherwise, you know, if you go to other places, you actually have to pay money to a tutor, right? It's still online, but our tutors are free to you. The OC Cares grant, I should check on it in case it's updated from last time. No, okay, but that is financial help for some of you, so you may want to look at that and maybe find a better link if I can't find a good one. And that gives you, you know, you get some money, helps you, you know, be at college. There's some notification, that's pretty much what it says. We're going to be doing today chapter 1. Today is horrendously long. There is no way in the world that either of us, me and you, we're going to use a single unit, is going to be able to do 3 hours and 40 minutes, because your brain will turn into sponge about halfway through that. So the way that we're going to kind of work this out is to try and break it up into little manageable chunks. And then I'm just going to give you some break time and some go online and maybe do some homework, and then you can come back and ask me some questions to do with it. So we'll be using this time to get your homework going. Now, if you haven't got WebAssign up and running yet, maybe during one of the breaks you can do that. And that's the link here, the one that says how to set up WebAssign. Do you see that link there? Now I'm just going to click on that one and we'll see what it tells you. You go to the WebAssign login page, which is this link here, you click on it. Our class has got a code, a class key, and it's this thing here. And then you follow some instructions like your name, your email, and some other stuff. And I believe you just basically, you should be able to log in. You're on 2 weeks free trial, but at the end of that 2 weeks, you need to buy a code. Basically, you need to buy to get into the class. And WebAssign is where we're going to be doing all our stuff. Now, here's fingers crossed. When I hit this, do you see a big PDF? Right. So all this PDF does is it kind of talks you through, hopefully the screens haven't changed too much. Right, so you would put our class key in, right, somewhere here. Then you get a little, is this the class you're talking about? And it'll have something like Math 146 in it. All of this is in Canvas, and you can then eventually join and you are good to go. So that's kind of the first thing that we would probably want you to do during one of our breaks. Just log on to WebAssign, get it going. Now, if you've already logged on to WebAssign, maybe what you want to do is go and try out some homework questions, and then when we come back, we'll go over some of those issues for you. Another thing you could do during one of our breaks is, since we're looking at chapter 1, if you click on chapter 1, I keep asking this, if it's not true, you just tell me. Are we looking at the screen that says chapter 1 now? Now, what you'll find here are 3 main sections. I've broken it into the videos, PowerPoint files, and notes on homework and so on. So if I click on this one, you see that there's a number of videos that you quick 8-minute, 4-minute, sometimes 10-minute videos that you can watch. So if you wanted to, for instance, get some more insight or some more information about types of data, you might want to watch this video. Here's some vocabulary and so on. So that's what that's for. If I kick into the second one, there we go. What you have here is a PowerPoint. and that's something that you can read over. And PowerPoints are very good, but I don't like using them too much because you get PowerPoint overkill. But it basically shows you some of the stuff, and you can go through it, just scan it through it. Gives you examples of strata. There should be more sophisticated ones, I'm sure, right? Systematic sampling and so on. Since we're on this one, let's just read it. Another popular method of sampling is called systematic sampling. In this method, it's assumed that the elements of the population can be arranged in some natural sequence. You could just basically take everybody's surname, and Aaron Aardvark gets number 1 attached to his name, right? And Zebediah Z gets 2040 if that's the size of your population. And then what you do is you just pick guy number 1, guy number 101, guy 201, 301, 401, and that allows you to go through a large group of people, but only picking a sample from them. And it's got a system to it, so it's called systematic. That's quite a convenient way of not asking everybody, especially if there's thousands of people and you don't have the funds or the time. You would choose a smaller group. So that's what's there. Go back to our home. And this is the web assignment schedule. So let me click on that. And let's see what's due this week. Chapter 1, essentially. Actually, there's a review to that, but let's pull part of it, right? So when you go into WebAssign, you will find that these guys are there. When you click on them, you get questions. Most of the time, at least for chapter 1, it's like 4 choices and you pick one, the correct choice. And sometimes it gives you a story and there's 5 or 6 things, and there may be 2 or 3 correct choices. Right, 2 or 3 things may also be true, in which case you click on all the ones that are true, and you work through it, and you'll get that one. When you do week 2, you see there's a lot more work in week 2. Essentially, what I've done is week 1, this stuff here, chapter 1, has to be completed by midnight on Sunday. Chapter 2, which we should get to today as well, with a bit of luck. Chapter 2. Won't be due until a week on Sunday, but I strongly suggest that you get started on those questions so that you don't have 8 sections to do in week 2. Right. So these ones will be due, right, not this Sunday, but next Sunday. So when you go on WebAssign, maybe this is a good time for me to jump to WebAssign. Are you clicking on WebAssign? Do you see the WebAssign now? Right, do you see Getting Started, which is a special one that just gets you used to our guys? There's 1, 2, and 3 I talked about. There's the review. Now, do you see that you've got 2, 1, 2, 2, 2, 3, and so on? Do you see these guys here? At least in my case, they're visible, right? So you click on those. You can do those so that you're ahead of the game, right? Try and get as much as you can, because sometimes your schedule 1 week's a lot quieter than the other. So if you can get stuff done, it means if you don't have a lot of spare time, you don't have much to do anyway, in which case it'll balance out. Okay, I'll pause for a minute. So far, so good. Right. How many of you, just do that little thumbs up thing that you can get on Zoom, how many of you have actually got, right now, WebAssign? Even if you haven't done anything, at least you've got it up and running. Right, 1, 2, 3, okay. There's a little guy down here on the bottom called reactions. If you click on that, you can do a thumbs up. Hey, just like I did, right? So that's just an easy way for me to do a head count. Hey, you found it, Chloe. You see it? The other one is when I tell really good jokes. Or not. I'm surprised they don't have a thumbs down, but maybe they don't want to make me feel bad. So you only get thumbs up or, yeah, that was cool. So those who don't have it, I strongly suggest that when we have our first break, that you go to Canvas and you try and follow those instructions. I don't think it takes long. Was it like 10 minutes? Yeah. So 10 minutes and you're done. And so when we have our first gap, we'll give you about 10 minutes to get that done. So what we're going to do now is, I can get started there. Where are you? You're here. You bear with me for a few more moments. Should be good. Right, now this lecture is going to be recorded, and you'll be able to get it on Canvas. And so if there's anything that I go over too quickly, or you can't quite remember what I said, then you can go back and find this video and you can check it out. So let's start with what chapter 1 is about. It's called Getting Started. Okay, I can handle that. I should know better. We'll come back to that. We're going to get started by doing some of the white screen. Here we go. And we're going to look at types of data. So this class won't be like a normal math class. You won't solve equations. You won't have x's. You won't really have anything that reminds you of Math 99. It's not that kind of class. What we're going to do is we're going to deal with statistics, and that'll be the first topic that I'll be dealing with. Let's wind back a little bit and give you a little intro. Statistics deals with data. And data is really just information. And we want to do things like, we need to collect that data. We need to summarize that data. We need to do graphical representation very often. Later on, we're going to do what's called inference prediction. So if you're looking at what you might call the statistical process, it involves us having a question. That question could be, I wonder who's going to win the next presidential election. That question might be, what percentage of high school students smoke cigarettes regularly? It could be, what's the average age of OC students? Right, so you got some question. And you have to collect data, information that's going to allow you to answer that question. So if I wanted to know who was going to win the next general election, then I assume what I need to do is ask people who they're going to vote for and base my, my answer on that. Well, you immediately collecting the data, you hit your first big hurdle. You cannot typically ask every single person in America who they're going to vote for. You physically can't do it, right? There's too many of you. It would cost a fortune, right? And even if you did that, it wouldn't necessarily be perfectly accurate. Couldn't you ask people who they're going to vote for and they say Republican, And then on the day of the election, they don't bother to vote. Right, so you're using their answer to make a prediction that ends up not being particularly valid. So what we typically do when we collect data is that we take a sample, which is a small group of people from the population. And we'll go into a lot of detail about how you try and make that as efficient and as accurate as you can, right? How you pick people to give you a good idea of what the heck's going on. And then you summarize the data. Well, imagine you went out there and you've asked 500 people who they're going to vote for. And all you've got is a piece of paper that says the first person said Republican, the second one said Democrat, third one said Royalist Party, right? You've got all this data, and it's just in a pile of paper. That's not very helpful, is it? You know, if your boss was interested, hey, who's going to win it? You say, oh, I went out, here you go. Here's 20 pieces of paper with numbers or Republicans or whatever the story happened to be, right? That's not going to do you any good. You have to summarize the data. And when you summarize the data, you can do it by having things that are called statistics. That's where the name statistics gets its name from. Some example statistics that you might know or have heard of are mean and standard deviation. I think everyone's heard of mean. You might have called it average, right? That's an example of a statistic. Now, you would use that if you were wanting to know, I know, the average age of OC students. Couldn't the average end up being 22.5 or something, right? That would be the mean. What you did is you got the ages of, say, 600 Olympic College students, you add them all up, and you divide by 600, and it comes out as that number. And that's your best guesstimate of the average age of all OC students. Now, provided you've picked a really good representative sample, it might not be perfect, but what it will be is pretty close to being, right? And that's all you ever get in statistics, unless you do a census, which means you ask everybody. All you ever get is, this is my best guesstimate of what you're asking me, right? What the right answer is. And if I do the job right, my estimate will be darn close to the real value. And if I screw up, it'll just be wrong, and you'll make conclusions based on that that don't actually make sense. Graphical representation, very often when you collect data, you make pictures of it. It's easier to see pictures than it is to see numbers. People visually can see trends and patterns, and oh, there's an awful lot of 27-year-olds at Olympic College, right? Whatever it might be, right? You can gather information like that and put it in a picture form, a graphical form. And the last one is called inference and predictions. Depends on the storyline, what that may be. An inference is just a fancy name for saying, okay, we found the average age of my sample was 22, so I'm going to make the inference that the average age of all those students is about 22 as well. And a prediction is more like, okay, we've asked a whole load of people who they're going to vote for, and our prediction is the Republican is going to win the next general election, or the Democrat's going to win the next general election. In other words, you make a prediction, I can't think of another word for it, on what you believe is going to happen based on your sample. So is there any questions about the kind of the big picture, how statistics does what it does? Okay, right, so let's look at types of data then, because I did promise that. So you ask a question and you go out there and you get your answer. Now your answer depends on your question. Your answer can take a variety of forms. For instance, if you were asking people their age, you would get numbers like, let's make it whole numbers like that, right? If you ask who they're going to vote for, you might get Republican, you might get Democrat, you might get Independent, right? You might get, I'm not telling you. I mean, that happens, right? People who don't tell you are called non-responders. You could get, well, what else? You do a chemistry experiment and you measure the temperature at 1 minute, 2 minutes, 3 minutes, you know, kind of a sequence of temperatures, and your answer comes out things like 14 degrees Fahrenheit, well, let's make it more likely, 74 degrees Fahrenheit, then it goes 80 degrees Fahrenheit, and you know, the next number is 90 degrees Fahrenheit, and so on, right? You got a whole load of data, and it's numbers, but numbers with temperature associated to it. So they have units, right? So far, so good. So for every kind of data, right, so this would be, I guess, temperatures. We kind of analyze the different situations, and we give names to different kinds of data. So this is the kinds of names that we use. Nominal, ordinal, interval, and ratio. Now, data that you deal with is going to fall into one of these categories, and each one has a kind of definition. This is what nominal data looks like. Nominal data is very low level. It's very often data that has, not very often, it is always data that has no order to it. To give you an example, if we ask people their favorite color, can you imagine that they might say red and green and blue? That data is correct, right? It is what I'm after. Maybe I'm after, what's the favorite color of people in America, right? What's the best color? What color do people hate? You know, whatever it is I'm asking. I've collected my data and it comes out to be red, green, and blue, right? And 42 like red and 12 like green, you know, as they accumulate it. But that data has no order. Would you agree if red doesn't come before blue, go before green? Couldn't you shuffle them and it wouldn't really matter? Very low level. There's not an awful lot you can do with nominal data. You can count what was the most popular answer. You can count what was the least popular answer, but you can't do much more than that. Okay, so that's what nominal data would look like. So examples of nominal data. Who are you going to vote for? Republican, Democrat, Independent, Royalist? I'm not telling you. Do you know there isn't any particular reason why one of them should be first or last? You could say, well, can't I just do things in alphabetical order? Well, I guess you could, but it's really not a true order, right? It's just a convenience. Something's not first, then next, and then third, and then last. There is no real true order to things like that. So that's what ordinal looks like. Nominal, I should say, looks like. Ordinal is a bit higher level. It's very like nominal data, right? The information you get can very often be things like words, red, green, blue, whatever, but they have an order. So, give you an example. If I went and said, if I was collecting data on university students and I wanted to know where they were, the answer I would get would be things like sophomore, junior, senior, freshman, right? Now, would you agree that they have a kind of natural order? Freshman first, I hope. Is it? Yes. Sophomore second, junior third, right? And seniors fourth. So can you imagine in that case, the information is still words. I'm a junior, right? The answer you get back wasn't 42, right? I'm a junior, I'm a senior. But it still counts, right? Because it has an order to it. And so that would be ordinal. A lot of ordinal data you get from questionnaires. You might even have had one. There's a type of questionnaire that has 5 levels to it. Right. And it goes something like this. You ask them anything you like, but let's do it from one order. You completely agree with the statement, or you somewhat agree, or you're not sure, or you somewhat disagree, or you completely disagree, I should say, completely disagree, right? Now that's a 5-scale level. Have you ever done, you're on the phone to your bank, and at the end they give you a little questionnaire that you come to the end, and they say, on a scale of 1 to 5, where 1 means you really, they did a really good job, and 5, you're dissatisfied. That's an example of this 1 to 5 scale. So ordinal data could simply be, which one of these 5 groups do you feel and you belong to for this question? So are you in favour of abortion? I'm not so sure. I'm kind of on the fence with that one. Do you, I'm trying to think, do you think Scottish professors should be paid more money than any other professor? In which case you would completely agree, right? Or you might completely disagree, but or you might be, I don't really have an opinion, so you have the middle. Can you see the difference between ordinal and nominal is that they both can be things that are words, right? I'm a junior, I like red, but red has no order. Colours can't really be put in any natural order, whereas I think something like that. Ordinal can also be numbers. Couldn't you just say, on a scale of 1 to 5, what do you think? So your answer would be, I'm a 4, I'm a 2, I'm a 1, right? So ordinal data can be numbers, right? Can be numbers, right? Okay. Now, interval data will be numbers. It has to be numbers. Before you even go anywhere else, it's got to be numbers, right? And then in interval data, you have another thing that you're allowed to do. You can subtract the two numbers. And the number you get makes sense. In other words, it has a meaning. Give an example. Suppose you were collecting information about temperature, right? So you're doing a chemistry experiment and you were getting 14 degrees, 28 degrees, 50 degrees, and so on. These are numbers, right? The units are just what it's measured in, but they are 14, 28, and 50. Clearly interval. Why? Can you subtract these and still have a sensible meaning? Couldn't I say that the difference between these two is 14 degrees? Right. The weather today compared to the hot, the highest temperature today compared to the highest temperature tomorrow might be 7 degrees. That 7 degrees has a meaning to us, right? It doesn't have a meaning in ordinal if you use numbers. Suppose you use a scale for 1 to 5. If you take somebody who says 3 and you subtract somebody that says 2, the number you get is 1. But it really doesn't have a meaning except to say, well, there's a difference of 1, right? It doesn't have any intrinsic value to it. So that's why that lives in the ordinal world, whereas temperatures live in the interval world. Examples of this kind of situation, right? Temperatures is a good one. Most of the best, the highest level, are ratio. And they are numbers, and you can subtract them. And you can also do ratios, which means you can divide one by the other. So let's give you an example of what ratio data would be. Do you know that I could ask a whole load of people, a whole load of students, what their age is? Right? Somebody's 17, somebody's 22, somebody's 50, right? I can subtract them and it makes sense, right? Two different ages. Oh, I'm 10 years older than you, right? You're 12 years younger than me. Subtraction works, just like interval. But if you are 60 and someone else is 30, can't you really say I'm twice as old as you and it makes sense to say that? A 60-year-old person is twice as old. That's the ratio part, right? I actually use that test when I'm looking at the difference between interval and ratio, because sometimes it's hard to separate them. I say to myself, suppose I had two numbers from this data set and one of them was twice as big as the other. Would it really make sense to say that? So yeah, it makes sense to say I'm twice as old as you are. I can be twice as tall as someone else. So height would be an example of ratio data. Great. Now, to show you why there's a subtlety here, temperature is not a ratio. And you might think, wait a minute. I could tell you that 28 degrees Fahrenheit is twice as big as 14 degrees Fahrenheit. And the numbers truly are twice as big. But the reason it's not ratio data is because these fellas depend on the units. Do you know if you convert these two things into degrees centigrade, they are not double each other anymore. So I'm going to choose two numbers that I know how to convert. 32 degrees Fahrenheit is 0 degrees centigrade, isn't it? And if I do 41 degrees Fahrenheit, I believe it is 5 degrees centigrade. If you divide 41 by 32, that's the ratio in Fahrenheit. If you do 5 divided by 0, do you see the ratio doesn't even make sense now? If you change Fahrenheit into centigrade, the pattern, the ratio between the two does not remain constant. Let's go back to height. If I said I'm twice as tall as someone, let's say I'm 5 foot and somebody's 2.5 feet. I'm not, but let's, for easy calculations. Yeah, I'm twice as tall as you. Do you know if I turn my height into inches, I'm 60 inches. If I turn 2.5 feet into inches now, different unit, oh, I'm 30 inches. Isn't 60 inches still twice 30 inches? Do you know if I converted my height into meters and the other person's height into meters, do you know you'll still be twice me? Do you see that ratio data is independent of the units used to measure it? In other words, it doesn't matter if you measure me in feet, inches, centimeters, whatever. The ratio will still end up being the same ratio in both cases. Can you see that in the temperature scale, that is not true? Right? If you have two temperatures in Fahrenheit and one's double the other, if you turn those same two temperatures into centigrade, can you trust me? They're not double each other anymore, right? The ratio between them has changed. Now, there is a temperature scale that some of you might have heard of that actually, if you use that temperature scale, you can then make your data ratio data. Degrees Kelvin. Because in degrees Kelvin, you have what's called a true zero. It's a zero that really means zero. You know, 0 degrees Kelvin means that thing has not got any energy left, right? It is pretty much dead, right? So units, if they matter, if changing the units that you measure something changes the relationship between two individual numbers, then you are looking at interval data. If changing the units, something is still going to be twice as big as the other, right? So the units don't matter. Then you're looking at ratio. And although that's a subtle difference, it can make a difference on how you interpret your answer, right? What statistics tell you you can and what statistics tell you you cannot do. And I think this would be a good point for us. Let's see if I've set this thing up properly. Right. Hopefully you're looking at chapter 1.1, what is statistics? Is that the screen you're saying? And it says, you know, questions 1, 2, 3, and so on. Nod? Yeah, nod is good. Okay, here it goes then. So we're going to introduce some of the other concepts by using some of these questions just to to give us an idea of what the heck's going on. So when you talk about an individual and a variable, what are we talking about in statistics? Well, an individual is one person from the population, right? So it might be me, or it might be you, one person, individual. A variable is a name that we describe to some aspect of the entire population. So a variable might be the average height of everybody in America. That would be a variable, right? The percentage you're going to vote Republican, that would be a variable. The amount of money, the average amount of money that people in Washington are worth would be a variable. The percentage of high school students who smoke cigarettes regularly, that would be a variable. In that case, the population would only be high school students, and so on. So in this question here, you basically get the question and then they give you like 4 choices. And the first choice is that an individual is the population of interest, which is not, so I'll stop reading. An individual is a member of the population of interest, so that's good, so I'll keep that. And then a variable is a numerical measurement describing data from that population. Next choice, an individual is a member of the population of interest. A variable is an aspect of an individual subject. No, it's not. And lastly, an individual, the population of interest, and a variable is a numerical measurement describing data from the population. And I am looking at that, and I'm going to pick the second one. You agree? An individual is a member of the population of interest, and a variable is some numerical measurement describing data from that population. Now, there were 2 types of categories for data that we didn't talk about, so this gives me a chance to do it now. We did talk about things like nominal and ordinal and so on, but we didn't talk about the fact that there's 2 big categories. One's called quantitative and the other is called qualitative. If your data is a number, right, 14, 42, it's called quantitative, quantitative. If your data is red, blue, green, Republican, Democrat, things like that, then you are describing that data as qualitative. In other textbooks, it's called categorical data as well. Now, I'm not obviously going to answer every question. Now, parameter and statistic. Let's look at that now. Suppose you have a population and you're interested in the average age of them. The average age is a parameter. It's a number that's connected to the population. A statistic is a similar number, but you only get it from your sample. So a parameter is a numerical measurement that you get from your population. A statistic is a numerical measurement typically you get from a sample. So for example, suppose I was interested in the percentage of students who smoke cigarettes regularly, percentage of high school students, I should say, who smoke cigarettes regularly. The population there would be high school students. The parameter in that case would be the percentage of those who smoke cigarettes. And then I collected a sample of 2,000 students, high school students. My sample would be those 2,000 students. My statistic would be what percentage of those 2,000 students said that they smoke cigarettes. So you see, it's the same kind of thing that you're measuring, but we call it a parameter when it's to do with the population, and we call it a statistic when that number is, you get it from the sample. Now, if things work out well, shouldn't both those numbers be darn close to each other? Your sample percentage should be very close to the true answer, the population percentage. Now here's an interesting question. For a set population, right, for any given population, does the parameter ever change? Well, I guess they could have made the question a little bit clearer. Suppose you have a population and you're interested in their average age. Then that's the average age of that population. It's not going to change anytime soon. So no, those things do not typically change. Parameter is a fixed number that is to do with that population, right? Now maybe over time things will change, but at that instant in time where you had your population in front of you, the average age is that number, and that's it. It never really changes. On the other hand, if I get a sample of 1,000 people and get their average age, and then I take a totally different sample of 1,000 people, would you expect that there's two samples to come out with the same number? No. Wouldn't you expect 1,000 people and another different 1,000 people to be a little bit different each time? Samples sometimes, or always typically, really, do vary. So that was a topic that we didn't really cover. Now, let's look at this one. What is the average miles per gallon for all new hybrid small cars? So that was the question that someone was interested in getting answered. And then it says, using consumer reports. So someone went and looked up, you know, my Toyota hybrid, what its miles per gallon were, right? And they collected some data. And they got a random sample of such vehicles. And their average came out as 35.7 miles per gallon. And the first question is identify who the variable is. And the variable here is miles per gallon, right? I guess you could say new hybrid small cars, miles per gallon, but it is still miles per gallon. Now, is miles per gallon quantitative or qualitative? So that's your question. Miles per gallon, is that a number or is it a thing?
It'd be quantitative, right?
Right, quantitative. The miles per gallon are just the units, right? It's a number, it's 35.7. Or, you know, the average height is 62 inches, right? It's just a number. And by the way, you can never be both. So never use that as your answer in any question. You must be one or the other. Now, it says, what is the implied population? I think they could have just said, what's the population in this story? Is it all cars? Is it just all new hybrid cars? All cars with average miles per hour, which is a bit silly, or new hybrid cars? Well, if we go back and we read the intro, it's the average miles per gallon for all new hybrid cars. You see it's there. The only people we're interested in finding the miles per gallon was new hybrid cars, new hybrid small cars even, right? We're not interested in all cars. We don't care what their miles per gallon is. We don't care what old cars' mile per gallon is. We're only interested in that small subgroup here. There's another story you could certainly go through in your own time. Here we get a chance to do some practice on nominal, ordinal, interval, and ratio. Right, so categorize these measures. They're associated with student life, so things that students would do. So the first one, the variable is the length of time to complete an exam. So which, and it can only be one of the four, the length of time. So it took me, on average, 87 minutes to finish my exams, right? Because I have more than one exam, so I'd go 87 minutes. That was my answer. Right? Somebody else it was 92 minutes, somebody else it was 50 minutes, right? Nominal, ordinal, interval, ratio. Any ideas? Okay, let's go through it in stages. Would you agree that that's a number? All right, it took me 52 minutes. It took somebody else 72 minutes, right, to do an exam. Check. So I'm not going to do nominal. Isn't nominal for just, red, green, blue, right? Now, I'm going to jump right to the end. If I took 80 minutes to do an exam and my friend took 40 minutes to do an exam, would it be sensible to say that I take twice as long to do that exam as he did? Is 80 minutes twice as big as 40 minutes? Right? Now, does it matter what units I used? Could I have turned those two numbers into seconds and wouldn't it still be twice as big as the other number? Yes. That makes it ratio. Do you see my little test? If I had two numbers and one was double the other, would they still remain double if you changed the units that you were measuring that information in? Right? So you changed it from hours to minutes or from minutes to seconds. Would one time still be twice the other in that new measurement scheme, right? So if I made it nice and easy, it took me 2 hours, my friend takes 1 hour. That's 2 to 1. Takes me 120 minutes, it takes him 60 minutes. Isn't it still 2 to 1?
I have kind of a silly question then.
Yeah.
But just to confirm, so if that always plays out, does that mean it's 100% of the time it's going to be ratio? Or could it?
If that 2, I'm twice you and it doesn't matter what the units are, that's how you tell ratio.
Okay, cool.
And if it doesn't work, it's probably going to be interval. Time would be interval, right? Couldn't you say, I took 14 minutes longer than him and that would make sense? And it doesn't matter if the units change. The difference would be sensible, right? It would have a meaning. The numbers might be different, but the definition of difference. Right, so, the time of the first class, right? My first class is at 1 p.m. And John, my friend, his first class is at 2 p.m. Does it make sense to say that his time for his first class is twice my first class? It's 2 p.m. double 1 p.m. Not really, right? So make it interval. My major field of study, mine is mathematics, my friend is English, and somebody else is geography. What kind of data are we collecting here? Mathematics, English, geography, and so on, right? What does that count as? I think someone said it, but I can't see it. So if you hit the space bar, I'll probably hear it. So the data is English, comma, math, comma, geography, comma, science, whatever it is. That's what you're collecting. What do we call that?
Nominal.
Nominal. Would you agree that it's not numbers, it's things, right? It's mathematics, it's geography, right? And there's not a normal, reasonable order to that, right? You couldn't say math is first and English is second and geography is third, right? It wouldn't make sense to put them in order. That's why it's nominal. If it would make sense to put them in order, you would go to the second category. You would call it ordinal instead. So nominal is like, it's things, not numbers. And the things don't have any natural order to them. That would be a typical nominal data set. If it's things, but you can put it in order, like, sophomore, junior, senior, that kind of thing, you could say in that case it was ordinal. Imagine you had data where you categorize people as being very poor, poor, average, rich, and very rich, right? Imagine you group people into those 5 categories. The answer you get back is you're rich, you're very rich, you're poor, right? That's what your data really consists of. But isn't that data got a natural order to it as well? Right, from very poor up to very rich. So in that case, it would be an ordinal data set. So do you see, you can be something that's not a number, right? A thing like I'm rich or I like blue. But in some of those situations, because there is no order, you call it nominal. In other situations, those things can be put into some kind of left to right, you know, small to big, whatever you want to call it, some type of order, in which case that would be ordinal. Here's one. Spring, summer, winter, fall. What's your favourite time of the year, right? That might be the question. So the answer you get back is fall, summer, right? Spring. Is that nominal, or is it a little bit better than that? Is that ordinal?
I think that's ordinal.
I would agree with you. What would be the natural order that you would do for the seasons, probably? Spring, summer, autumn, winter, for instance, would be a pretty natural order. You agree? There is an order that you can do to some things, and that stops a nominal, that upgrades a nominal to an ordinal, right? So let's look at D now. Course evaluation scale, where you evaluate your professor and you can say it's poor, it was acceptable, it was good, right? Let's say it was your professor, it could be you that's getting evaluated. So your answer is simply going to be one of these three categories, right? So doesn't that restrict you to only having the two top choices, right? If you ain't a number, you can't be interval and you can't be ratio, right? You must be one of these two. Does that list have a kind of natural order to it? Poor, acceptable, good? Yeah. In fact, the way it's written is probably the order you would use, right? Poor, then acceptable, then good. So that makes that data ordinal. We're a bit like a nitpicky lawyer here. Do you see what we're taking something and we're trying to categorize it into one of four categories? It must be in one of them. It can't be in two at the same time. It has to qualify only in one. And we're trying to figure out which category that is. The score on their last exam, right? So you got a whole load of people and John got 42 in the last exam and Mary got 90. So that's numbers, agreed? Percentages, numbers don't matter, it's still a number. Interval and ratio are the choices now. Now I can certainly subtract the two numbers, but an upgrade to that is ratio. Does it make sense to say that Mary got twice as many points as I did? Right? She got 90 and I get 45. Yeah. In this case, there are no units. Would you agree? You just get 90 out of 100 or you get 45 out of 100. And if there is no units to it, it kind of makes your life easy. Because if there is no units, it's kind of guaranteed to be ratio, isn't it? And it does have what's called a true zero. Couldn't you theoretically get 0 in an exam? And it would make sense. Okay, last one. Hopefully we've got the idea of what's going on here. Age of a student. Which one of those four categories does the age of a student fall within?
Ordinal?
Well, what kind of numbers would you get? You'd get, I'm 42, I'm 17, I'm 20, right? It's a little bit higher level than ordinal.
Maybe interval.
Ratio?
It's actually ratio. Let's see if that works. If somebody is 40 years old and another person is 20 years old, right? I'm doing that, you know, double test that I like to use, right? Somebody's 40, someone's 20. I'm twice as old as that person, right? 40 to 20. That's 40 years compared to 20 years. Suppose I went and turned my age into weeks or months or hours or seconds. Do you know I'd still be twice as old as you? Right, so it does qualify as ratio. Ordinal would really just be a number that you would get that has some order to it, but you can't really divide or subtract them. Ordinal, when it's a number, would only be that on a scale of 1 to 5, 1 you hate it, 5 you love it. What do you think of this TV show? Right, that kind of question. The answer is a number. It does have an order, but it doesn't make sense to subtract a 3 from a 1 and say that difference is a 2. It doesn't have any real meaning. Whereas if you can subtract them and it has a meaning, you have interval. And if you can divide them and it stays the same no matter what the units are, you're now ratio. And I am finished with that, and we are now going to return and look at our next topic. Is there any questions about types of data, which is essentially what that section was dealing with? If we get any questions on that, are we good to move on? Okay, so what's our, oops, I didn't do it. Here I go. So what we're going to look at now types of samples. Errors in sampling. You're going to have to, in almost every situation in the statistics, you're going to have to collect a sample. And a sample is a small group of people from the population. So a sample, right, is a small group of people who come from that population. You want your sample to be a fair representation of the population. And that's actually a very difficult thing to do well. You can't ask everybody in America who they're going to vote for in the next general election. There are just too many Americans. It would cost you a fortune. In fact, to be able to do it, wouldn't you need to know every person in America and where they stayed? You'd have to have their names and addresses, wouldn't you? And you'd have to, I guess, spend millions and millions finding every single American and asking them. When you do that, when you ask everyone, so if you ask everyone in a population, we call that, in statistics, a census. Even although America is one of the richest countries in the world, do you know that we only do censuses? That's, they call it that. Don't they only do it every 10 years, typically? They have a few minor ones, but the big one, where everybody gets asked, only happens every 10 years. Can you imagine how expensive it is to do a census? That's why only governments can even afford to do it. Right? You have to hire, literally, hundreds of thousands of people on short-term contracts to go around and collect censuses. And you also send out censuses, you post them, you do it every which way you can. Extremely expensive. You can't really do it much. So we're stuck with a sample. So how do you get a fair representation? Well, let me go back to who's going to win the next election problem. Let's suppose that I ask 1,000 people. We typically use the letter N to mean the number of people in your sample. So ask 1,000. And I just decide to ask 1,000 men. Would that be a fair representation of the voting population in America? It's a kind of silly question. Agreed. It's, yeah, slightly more than half the people in America are women, right? And I'm not even asking any of them. Why would that be important? Well, sometimes it doesn't matter. You know, some things it really doesn't matter if you're a man or a woman. You all like or dislike roughly about the same. Not often, but sometimes that's true. But in voting, it isn't true. Do you know that men and women do vote differently? It's not that all men vote Republican and all women vote Democrat, but more men vote Republican and more women tend to vote Democrat. It's just the way things are. So you would certainly, if you were going to do a sample, wouldn't you want at least the same number of men and women, roughly, in your sample? That would keep it fair. You'd get a good balance of what males and females think about the election. Here's a strange one. Can they ask me personally, could I be in that sample? Well, the answer is no, I shouldn't be in that sample. I'm not allowed to vote in America. I am not a citizen. I'm a permanent resident, and permanent residents don't vote. At least they shouldn't, and I certainly have not. So when you ask people in your sample, don't you have to make sure that not only do you have 1,000 people, roughly equally balanced males and females, don't you have to also make sure that you only pick people who are allowed to vote in the first place? Because that would distort your information. So we're going to look at types of samples, right? On how you can at least attempt to do a fair representation. The first kind of sample, and it's called a simple random sample. Well, in a simple random sample world, every member of the population has an equal chance of being chosen. To be in the sample. So if you want a simple random sample, every single person in that population has to have an equal chance of being chosen to be in that sample. Sometimes, I wish it was more true, sometimes you can actually get a simple random sample. It's considered in statistics the best sample in the world. That's the ultimate holy grail. Can you make that happen? Many times you can, in which case you have to resort to, we're going to show you other sampling techniques. But if you can, you should. Give an example how that might happen. If the population's not too large and you know enough about them, you can probably do it. Suppose we look at Olympic College students, and I'm interested in your average age. Right? Well, I've got, or not personally, but this college has got a list of every single Olympic College student. What you can do is you can go to a computer and just say to the computer, randomly choose 1,000 people. And then what the college might do is they send you out a little questionnaire and you fill it in, and one of the questions is, what's your age? If they're going to spend that type of money, they tend to not just do it for one question. You know, has any of you ever done one of those? We do them quite regularly in the college. Did you ever get a form where you had to fill in things like your name and your age and how many credits you took and what's your major? I think it's called the college something survey. I can't remember what the middle word is. Right. That's what we're doing there. We're collecting simple random samples. You might be thinking, why did I get chosen? You get chosen randomly very often. Sometimes it's your class that gets chosen randomly. Well, that's a simple random sample. And that's one of the possible types of random sample you can get. I think what I'm going to do to make my life a little bit easier is I'm going to go to our PowerPoint, and we can use it because it's already written down somewhere. I think it's this one. Nope, not yet. Where are we? Is it this one? Nope. I'm going to have to get good eyes one day. Not quite sure how that's going to happen, but I'm going to have to do it. Third time lucky. Where are we going with this? It's not that one. It's not that one. It's not that one. The only one I haven't done, the second last one, it's that one. Yay, we got it. Okay, so I'm going to kick back here. I'm going into getting started again. We're going to go here. And we're going to use this guy. And it gives me a chance to talk about a random sample. So that's the formal definition I just gave you of what a simple random sample is. They make it a little bit more legalistic than it needs to be. And they go into some details that I'm not going to. It's essentially to do with simulations of how you can make that happen. And now we can move on to here. So one different version of a sampling technique is one that's called a stratified. I'm writing that down. Sample. Now, what does that look like? Well, groups or classes inside a population that share a common characteristic are called strata. And for example, in the population of undergraduate colleges, you might have the 4 groups, the freshman to the senior. Other strata might be men and women. Other strata could be states that you happen to live in. So you take your population and essentially you break them down into little groups. Whatever, you choose the groups depending and very often on the question that you're interested in. So maybe the groups are men and women. Maybe the groups are which are you, a junior or a senior, right? Something like that. And then what you do once you've broken those into groups, you then do a simple random sample of a certain size from each of these groups. Okay, so let's put a story together. Let's suppose I was interested in, back to my usual guys, who's going to win the next election? And I've decided that males and females are important and rich and poor are important. So what I do is I break the entire population of America into 4 groups. And the 4 groups would be males who are rich, females who are rich, males who are poor, females are poor. So you see I've got 4 stratum, 4 groups. I'd call them groups, but strata, right? 4 groups. And for each one of those groups, I choose 1,000 people. So I find 1,000 rich males. I find 1,000 poor females, right? 1,000 in each of the 4 groups. Random sample. And I ask each of them, who are you going to vote for in the election? That would be an example of that stratified sample. Another story. Suppose I was interested in people who work in hospitals' opinion on abortion. My strata here might simply be men and women and hospitals. So there's, who knows, there's 2,000 hospitals in America. So I would pick a couple of them randomly. And then within them, I would randomly pick men and women. And so I would get a kind of sample based on those strata. Now, the next one in this list is called systematic sampling. Right. Now, in this method, you take everybody in the population and somehow or other you found a way to put them in order. So if we were doing Olympic College, what you might simply do is put people in order according to their surname, right? So Aaron Aardvark is number 1, and Zebediah Zebra is number 6042, right? And that's every student in America has now got a number beside them, right? Guy number 1, guy number 51, and so on. And then what you do is you just pick somebody, let's say you pick the first person, and you ask them the question, whatever it is, and then you pick guy number 101 and ask that person. Person number 201, 301, 4, 5, 6, 701. Do you see, in that way you could get a sample, and it's not quite random. Do you know there's a system to why you pick the person, right? It's every 100th person after the next one. So you don't ask everybody. You're basically only asking 1 in 100, and you're going through the entire population that way. That would be an example of a systematic sampling. Now, to do that, you really do need to know everybody in the population, and you have to be able to put them in order, but you could do it. Another example of that. Suppose you were interested in the opinion of people in your street, and you live in a very long street, right, with lots of houses in it. Couldn't you just simply pick house number 1, house number 11, house number 21, house number 31, all the way to the end of the street? And that would be a small sample of your entire street. That would be an example of systematic sampling. So you'll recognize that in the story that they give you when there's I pick somebody and then it's every 10th, 100th, 1000th person after that. That's the key that tends to tie these kind of things together. The next one is going to be called a cluster sample. This one is extensively used by government agencies. The government agency has lots of money, so they can afford to do sampling techniques that are quite time intensive and very big. So how does a cluster sample work? Well, basically you divide the entire population into some demographic way. I'll give you an example they probably do. Forgot what the number. Is it 50 states in America? Is there 50 or 52? I've forgotten. Anybody want to volunteer that number just so I can be accurate?
It's 50.
It is 50, and that includes the District of Columbia probably, right? So nice, I should have remembered that. So there's 50. So you have broken America into 50 different states, right? Alaska, New York, all the states. And then what you do there is, after you've done that, you randomly select sections or clusters from each of those. So you can imagine that you've got all 50 states, and then inside every 50 states, you're only interested in something to do with school children or something to do with old people. So what you do is, in that state, each state, you get 100 old people and you ask them the question, or 100 teenagers in high school and you ask them that question, right? So your sample is a little random sample. Every single random sample comes from one of those states, and you put them together. But what you have to realize is that when you do these types of things, let's give you a better story, in my opinion. Suppose we go back to, I'm interested in people who work for hospitals' opinion on abortion. What I might do here is separate my clusters. In this case would be every single hospital in America would count as its own little island, like its own little state. I then randomly pick 10 of them, and I go to those, but I don't just select a group of them. I ask everybody in that hospital. So if I pick 5 hospitals, I ask every single person. And that is an example of that. type of doing. The next one's called multi-stage. That's basically you do a bit of A and a bit of B. The last one really should never be done, but is done far too often. It's called a convenience sample. It's basically you collect the data by simply making your life easy. It could be this. This is an example of convenience sampling. I go to a mall with a clipboard and I stop the first 100 people that pass me by and I ask them who they're going to vote for. That would be an example of a convenience sample, right? A convenience sample could be that I go to a phone book and I randomly pick 200 people and I phone them and I ask them, who are you going to vote for? Right? There's not an awful lot of planning or thought to this. Do you see? It's very simple to do, it's easy to do, and it is fraught with lots of dangers. And we're actually, once we finish talking about this, we're actually going to look at some of the problems involved in sampling. And convenience sample tends to be the one that causes the greatest amount of errors in your results because of the very poor way in which it is done. Now, there's a lovely little summary here, so that when you're doing your homework in 1-2, if you find this page here, you might want to have it handy because it'll allow you to do those stories where they say, here's a story, what kind of sampling is going on here? And you can see it's random, stratified, systematic, cluster, multi-stage, and finally convenience. Now, any questions about the major types of sampling that we talked about? Okay, so let's talk about what can go wrong. You can do everything correctly and still screw up. Your data will be in some way incorrect. We tend to use a word called bias. So your sample can be biased in some way. Now, there are a number of ways you can do this, and in no particular order. You can underestimate in your sample, what underperform, there's various names for it. If your sample, for some reason, does not contain a fair representation of the population, can you imagine that the answer you get won't be as accurate as it could be? Right. So, underrepresented.
Could we see your notes?
Oh, I
Sorry.
forgot. No, I'm glad you told me. I'll put it back up and I'll do it again.
Thank you.
Did you not see me writing all that other stuff when I was talking through because of that?
No, I think it just showed the PowerPoint.
Right. Okay. That's what I was writing down as I was talking, but the PowerPoint has those same guys, so you can actually get that. But now it's here, you can, if you watch this video, you can go to there. So now we're looking at bias in our samples. So bias in sampling. First one, underrepresented. Give an example. Suppose you do a phone survey. So you only ask people who have a telephone and you phone them up and you randomly pick them, so that's pretty good. In fact, you might even do a random sample of phone owners, but that is not the entire population. Won't you miss people? What kind of people would you miss? And don't overthink this. What kind of people would you miss in a phone survey?
People who don't have a phone.
Yeah, people who don't have a phone, right? It's not meant to be a trick question. You miss people who don't have a phone. Now that could be big. Suppose 10% of Americans don't actually own a phone. Just making that number up, right? Suppose you just don't own a phone. What's the main reason people don't own a phone? I know there's lots of reasons, but what do you think is the most likely reason for people not owning a phone?
Could
They
be
don't
age
have any cash
related.
money.
Could be, okay, yeah. Let's talk about adults. So that's true. But what would be the main reason for adults not owning a phone?
They can't afford it.
Can't afford it. That would be my guess, right? And that's a reasonable assumption, right? Now, wait a minute. Do you know that people who are, for want of a better word, poor, do you think they vote Republican and Democrat the same way that other people would? Or do you think there might be more Democrat voters within the poor group than Republican voters, just for argument's sake, right? Can you see that you've now collected a sample that is underrepresented with poor people? And therefore, the answer you get might not be as accurate as how many Republican stroke Democrat voters there are. You see, that could cause a big problem. Underrepresentation. We even have some jargon, so I might as well put that in here while we talk about that. We call this thing called the sampling frame. The sampling frame is the people who could be in your sample. Now, you don't ask everybody that could be in your sample, but the people who could be in your sample are called your sampling frame. You would want that to be the population. If you possibly can, that's what you want, right? But sometimes you miss people out. So in this case, can you see that the sampling frame would only be people who have access to a phone? And it's not the same as people who can vote in America, right? It's not the population. So that is one of the reasons your data could be wonky. Here's another way in which your sample gets biased. They're called non-responders. When you ask people sensitive questions, you very often find that they don't want to answer, and they've every right not to answer, right? We're not in a police state where you have to do what I tell you, right? At least not yet. So we're non-responders. They're people, you ask them who you're going to vote for, and they turn around and say, it's none of your darn business who I vote for, right? Who I vote for is between me and the ballot box. That's a totally respectable and understandable response. But let's suppose that 20% of your sample are non-responders. Now, if that 20% who don't tell you are pretty much balanced, right? Republicans are just as likely to say, I'm not going to tell you who I'm going to vote for as Democrats, then that won't really cause a big issue, right? Can you imagine that won't be a big deal? But can you imagine a world where maybe Republicans don't feel comfortable with telling you they're going to vote Republican? So couldn't this non-responder group be weighted 15% Republican, 5% Democrat? And can you see that that will make your estimate a little bit out? You won't get quite as many Republican people as truly would vote Republican. It's quite a hard thing to deal with. If it's only 1% of your sample, do you know you can probably say, no biggie, it's not going to make that big a difference. Even if every single one of them was a Republican or every single one of them was a Democrat, it's only going to be a 1% out. And you know when you get your answer, you never get it perfect anyway. It's going to be 52 Democrat, give or take a couple of percent, right? That's what your sample ends up telling you. So it's not a big deal if it's small. It is a big deal if it's large. And the people in this group may be more weighted to one or the other. Non-responders. One more missing word. People who, insert word here, can cause problems when you collect data. People who do what? Let me give you a clue. If you ask people very sensitive questions, like, have you ever been in jail? Have you ever been unfaithful to your wife? Do you regularly take illegal drugs? Right? Very sensitive questions. Do you know what sometimes happens? Actually, probably happens a lot. People do what?
They
They
lie.
Well,
lie.
Right. They could be non-responders, but we've covered that. They can lie. Never touched a drug in my life. Never been to jail. Never been unfaithful to my wife. I think it's time for a joke. We've been at this almost 2 hours and we need a joke. I need a joke. Are you ready? I need to see some hands up there. Okay, we got it. Right. So I'm going to close this off for a second. And I think it's helpful for your brain just to have a little breaks, right? Just changes. It gives you, it makes you a little bit fresher when you come back. Although after this joke, I'm not so sure. So this is a Scottish joke, as many of my jokes can be. And it's about a Scotsman, an American, and an Englishman who die and they go to heaven. And when they get to heaven, they're looking around and the place is wonderful. It's a really beautiful place. And the Scotsman's really excited because it's huge. Heaven is big. And St. Peter was giving them a walk round and the Scotsman gets dead excited and says, look, heaven's really big. And says, how do we get around? Do we get a car? Do we get a car when you're in heaven? And St. Peter says, of course you do. You get a car. It's too big. You can drive. You get a car. And the Scotsman said, do I get any car I like? Can I get a sports car? Can I get anything I like? He says, well, it doesn't quite work that way. He says, well, how does it work then? He says, well, we have to ask you a question about your life and it depends on the answer what kind of car you get. And so the three of them are saying, okay, what's your question? So he says, well, here goes. He goes to the Scotsman and he says, how many times have you been unfaithful to your wife? And the Scotsman says, I've never been unfaithful to my wife. St. Peter's got a little book and he says, yep, we know the answer already, you're right. So the Scotsman says, what kind of car do I get? He says, you get the top of the line. You get this big fancy convertible sports car, right? Boom, it appears. He jumps in, boom, drives off. And he goes to the Englishman and says, your turn. How many times have you been unfaithful to your wife? And the Englishman said, only once. And she forgave me just once and never did it again. And he looks at the book and says, yep, you're right. And the Englishman says, well, what kind of car do I get? He says, well, you're not getting the same one as the Scots guy. We're just going to give you a normal standard four-door Ford. Boom, it appears. And he gets and drives off. And they go to the American and they say to him, he says, well, how many times have you been unfaithful to your wife? And he gets kind of shy and he doesn't want to tell them. And he says, look, we already know it. You got to tell us. He says, 42 times. And he looks at him and says, 42 times? He said, yeah, 42 times. He says, it's a miracle you got into heaven. He says, yeah, I don't know how I done it. It was a miracle. Made it. He says, well, what kind of car am I getting? He says, well, for 42 times, you're getting the worst one we've got. And this guy's about 6'6". And what appears is this tiny Mini with flat tires. And the windows are all broke and the windscreen's cracked. And he squeezes into it and he drives away. Well, the next day they're at the traffic lights and the Scots guy pulls up in the middle and the American pulls up in his car and the Englishman pulls up in this and they're looking and the poor Scottish guy's crying his eyes out. He's crying away. And the American looks at him and says, what are you crying at? Look at the car you've got. Look at the one I'm driving. Why are you crying? And the Scots guy said, well, I just saw my wife and she's using roller skates. There. You liked that one? Okay. This class isn't as bad, right? I know it's 3 hours and so many minutes, but at least we break it up occasionally, right? Now, what might have happened, and I would be surprised as it has, people who lie, which is where that joke came from, right? Made me think of that poor guy, right? So that is a big problem. It's very difficult to tell if someone's lying to you, so you can't really predict it very easily, but you know that it's most likely to happen in very sensitive questions. If I said to you, what's your favorite color? Would you agree that the percentage of people who lie to that question is minuscule, right? I can't see any reason for you want to lie. On the other hand, if I went and asked you about taking illegal drugs regularly, would you agree that a question that's as sensitive as that, or have you been unfaithful to your wife, those ones would probably get larger response rates that are lies? Agreed? So how do you try and minimize lying when you're asking someone very very personal information? Right? It could be about their sexuality, it could be about their finances, it could be about their drugging, whatever it is, right? How do you do that? I'll give you an example. Suppose we were interested in what kind of drugs high school students are taking, right? We're talking illegal drugs here. What kind of drugs, are they taking? What's the names of them? If they're doing prescription drugs, what, are they doing, the opioids? What are they doing? If you just went to a high school and gave the students a questionnaire to fill out in class, could you imagine that that's going to generate an awful lot of lying? Right? A lot of students are not going to tell the truth sitting in the room with a form where you have to tick boxes, which drugs have you taken in the last month, right? It's very difficult. So how you get around that is that you try and make sensitive information that you're collecting as anonymous as possible. So one of the ways you could do it is each student individually goes into this room and there's the form that's there. You tell them in the form, none of this information can be traced back to you. Your name's not on it. When you're finished, you fold it up and you stick it in a box where everybody else's answers are. You can give a good shake if you don't trust us, right? It's done, right? You also try and tell people why you're collecting that information, because that can very often help them to feel that there's a reason why they need to even bother telling you. So you would explain, look, we want to know what these drugs are because we want to make sure, we want to see what kind of drug trends there are, and it'll allow us to be better prepared for treating people who overdose on certain drugs. So if you know that the new drug of choice is some kind of opioid, you're going to tell doctors, watch out for students who take or OD on this drug. This is the kind of symptoms they're going to have. This is probably the drug that they've taken. And when the ambulance comes and all they have is an unresponsive teenager there, it's kind of hard for them to know what the hell they've been taking. At least you might be able to plan ahead a little bit and save someone's life. So you would do it for those reasons. And if you're talking about, people's sexual behavior, you would explain to them that you're interested in sexually transmitted diseases and we need to know how many partners you're likely to have had and what those partners are like and so on, so that we can get a better information. And again, you make it anonymous, and if you do it well, you can actually reduce the lying quite a bit. So you can underrepresent people. You can have non-responders or not telling you. You can have people who lie. You might wonder why that's in my list of how you can bias a sample. How you ask the question. I'll give you a very crude example of that. Suppose I was interested in people's opinion of abortion. It's a common topic I picked. And I say to you, are you in favour of a woman's right to kill an unborn child? You can tell that's a really bad question, right? But can you also tell that if you phrase it that way, you may influence someone's answer? People don't like to be thought of as being bad people. So isn't there a tendency for you to answer it the way you would think people would want you to answer that question, right? So if you bias it in that way, people are going to say, well, of course you don't want unborn children to die, right? So I'm not that in favour of abortion, right? You influence them, or you can influence some people at least. You could have asked the question, are you in favour of a woman's right to choose? Now, you might think that's not biased, but actually, to one group of people, that is very biased, isn't it? Right, pro-abortion and anti-abortion people, right? They're pro-life and pro-choice is typically the labels they put on each other, right? But can you see that that second question is more likely to influence people to be more likely in favour of abortion than not? Actually, if you wanted to ask that question, shouldn't you just say, are you in favour of abortion? Shouldn't you keep the question simple and direct and don't have any influence in the way that you ask it? Now, a lot of people who run surveys and questionnaires and politicians are big versions of this. They do it a lot. You know, they ask questions when they pay for the survey or the poll. They very often get the questions to be asked in a way that favours their viewpoint, so that they can say, well, we conducted a poll and 82% of people are in favour of whatever it is. I could do that right now. Suppose I was interested in getting people to be in favour of higher taxes, right? So I wanted them to say yes to that question. Instead of just saying, are you in favour of higher taxes? I said, do you know that the government spends half as much money on the poor as most Western countries do? Are you in favour of raising taxes so that we can spend at least as much as the Europeans do? Now, you see the way I phrase that question is I'm trying to push you along that, yeah, I think we should have more taxes, right? Now, if I wanted you to be against taxes, in other words, reduce them, do you know, I could say something, do you know that 20% of all the money that the government spends is fraud? People steal it. Do you think we could reduce tax, then go and ask them about taxes? You'll be thinking, oh, why am I giving them more money if 20% of it ends up getting stolen? And we don't mean they go into a bank and steal it. You know, people fill in forms and apply for things that they don't really qualify for, and so on and so on. And that's kind of what the fraud that they're talking about. Medical fraud is rife. Do you know that there's groups out there who build, oh, that's weird. There we go. So we're now on to section 1.3. This is the last section in chapter 1. Once we've done this one, we'll start on chapter 2, at least give you a heads up on it. And that will be us for this week. So just to remind you again, this Sunday you have to make sure that chapter 1, including the review from chapter 1, is complete. There's not that many questions. If you go in and look, it's number-wise, there are not that many. And try and get as much of section 2 as you're up for as well, so that next week it's not overwhelming. Well, what is experimental design? Essentially what we're going to look at is, in a little bit more detail, how we collect data for very often scientific purposes. So if any of you are in the medical field, if you're going to become nurses or do something to do with the medical side of things, then this is going to be the most common way that you will see information directed towards you. Experimental design is basically how do you organize the collection and interpretation of your information to come up with good conclusions. There are only 2 versions of it. The first one is called an observational study. And these types of studies are quite common in medicine. What you do is that you have no control over who the groups are, who the people are. you just observe them. So an example of an observational study was the one that was used to prove eventually that smoking was bad for you, right? It caused lung cancer and other things, right? And so what they did is they collected data on lots of different people. Some smoked, some didn't. They just went to doctor's records, and gleaned out that information, and they found out things like when they died, what age they died at, and what they died of, what was the cause of death. And they built up a pretty good set of knowledge here on that there was a very strong connection between people who were heavy smokers and early death, and people who were early smokers, not just early death, but the things they died of were quite heavily in the lung cancer, connected to your blood pressure and so on, right? Not that many of them die diabetes or anything, right? Or, cholera or something, right? So they looked at that data, but they didn't have any sampling technique. They basically just observed things. So an observational study could be something like this, where someone watches a whole load of children play, and they look at the children and they record how many times a child hits another child. Children hit each other, not violently, but they do, right? And they record this data, and they record it for each child. John hit 4 kids. Mary didn't hit anybody, right? And maybe they also recorded who was hit. John was hit 8 times. Mary was hit 3 times, right? That kind of information. But it was totally observational. They just watched. And they didn't do anything about organizing any kind of study. They just interpret the information. Observational studies have to be done in many medical situations, because the only alternate to that is a controlled experiment. In a controlled experiment, what you typically do is you have 2 groups. Call them group 1, say, and group 2. Group 1 is called the control group. And group 2 is very often called the experimental group. So let's put a story. Suppose we are interested in the effectiveness of a new pain-killing drug, right? So what you do is you get a random sample of, say, 200 patients. And 100 of them go into the control group, and the other 100 go into the experimental group. Now, the control group people, they either get what's called a placebo, or they might get the old drug. Depends on the situation. Has anybody heard of the term placebo? It's a very interesting effect if you've not heard of it. Placebo effect essentially says if you give someone a pill and you tell them it's going to reduce their pain, if they believe it strongly enough, they will actually have a physical experience of less pain, right? It won't hurt quite as bad as it did without the pain. Even although the pill you give them is a sugar pill, it has no medical value at all. The sheer willpower or the strength thing is capable of doing that. The mind is a wonderful thing. It can be controlled in many ways, and pain can be very subjective. You understand that we're not talking about your arm cut off, that's painful, right? But we're talking about, I've got a kink in my back, I feel some pain there, right? Pain can be very subjective. And your brain is kind of in charge of what it is telling you about the pain level that you've got. And if your brain thinks that it's not that bad, it won't feel that bad, right? In fact, there are some very remarkable people who can actually, for want of a better word, self-hypnotize themselves to feel no pain. as long as it's not a major operation, right? They can self-hypnotize themselves and they can have their teeth extracted and they won't feel a thing, right? Have you heard of those kind of people, right? So it shows you the power of the placebo effect. Most humans are not that good, but it does have an effect. So to not have that take place, we very often give the control group a placebo. They give them something. And then we have an overarching thing that's called a double-blind experiment. Most of them are. Double-blind experiment is when the people who are in the control group or the experimental group, because the experimental group, they get the new drug. But none of these people here or here know which they're getting. They don't know if they're getting the new drug. They don't know if they're getting a placebo. In fact, they don't even know it's a placebo, right? They just know they're getting a pill. The second half of the double blind is that the doctors, because very often this is done through doctors, right? You go to your doctor and it says, right, you're part of this new trial, right? This new medical trial. And he gives you the pills and he then checks on how your health is and what your pain levels are like. That doctor doesn't even know what pill you've got. And I can understand in a way why placebo effect works on people, right? If you take a pill and you're told it's a really strong pain medicine, it might well have an effect on it. The less obvious one is why the doctor shouldn't know either. And they discovered that the doctor didn't tell people. You know, he didn't cheat and say, by the way, you know this is a sugar pill. It's not doing any good. Right? They don't do that. But subconsciously, they still convey that message. You know, when your doctor asks you things, he might say, how is your pain level? How are you doing? You know, he gives it in that concerned voice because he knows you've got a sugar pill, right? And he knows you should be in pain. You see, he can indirectly influence you. So that's why doctors aren't allowed to be told in a double blind. You don't know what pill you're getting, they don't know. They then look at the results. And if this group has a higher success rate, then you have got evidence now that that new drug is better at relieving pain than no drug at all, or more typically the old drug. So when a new medication comes online, one of the things you have to do is prove its effectiveness, right? Now that's a drug one. Can you imagine it's a chemotherapy, it's a pill that you take during chemotherapy, and it's to reduce the death rate because chemotherapy is severely taxing on a weak body, right? You can die of chemotherapy, you can die of the treatment, right? It can kill you. And so very often they want to protect you as best they can, right? So you very often get medication to try and subdue some of the nasty side effects of chemotherapy. So can you imagine that would be the new one? And they would look at things, so what's success rate? Well, in chemotherapy, it might be the new pill, instead of having a 15% death rate, we only have a 10% death rate, right? It's not perfect, but it's better. That would be a sign of success. Here, it might be a larger number of people said that they had a bigger reduction in pain, right? Pain's a very subjective thing. Do you know how they get children, changing the subject slightly? Do you know how you get children to tell you how much pain they're in? Because they're not very good at words, right? Do you know they've got a little chart with little pictures where on one side it's a big happy face because I ain't got any pain at all, and then it's kind of frowny face, then it's I'm weeping, right? And the kid basically looks at it and says, that looks like how I feel. And they have a kind of scale like that. When you do adults, you can actually, asking someone, how much pain are you in? Do you know it's very subjective? I'm in a lot of pain. Well, what does that mean? Can you put a number on it? Okay, we'll give you a scale of 1 to 10. 1, you're not feeling any pain at all. 10 is, just kill me now, right? That's how much pain I'm in, right? Just get it over with, right? And you know, you could have a kind of scale system. And you can come up with the results of that. So when this happens, what then typically happens is it gets published in a medical journal. And there's tons of medical journals. Some are very, very precise. There's probably a medical journal that only deals with pain relief. So when you write a paper and you've collected your data, you publish it to them, right? Okay, and what will then happen is that it gets peer reviewed, which typically means people will look at the way you designed your experiment to make sure that it was done well. Was it a double-blind experiment? Was was everything done the way it should be? Then the next stage is that other doctors or other hospitals say, we would like to repeat that experiment. We'll do it again. And you do it a second and sometimes a third or a fourth time. And if every single time you keep coming back with, this guy works, this guy is better than the old guy, that then becomes a new pill that people take for pain relief. And that's kind of how it gets in the market. Now, there are other things like they check it's they check that it doesn't kill you, side effects and all that other stuff. We'll assume that it's past those. Medical people, pharmaceutical companies have to go through a very rigorous process of proving that their medication is an improvement on the old one. The FDA basically says, it's no good that your pill does just as good as the old one that we've got. We won't let you use it because we don't know the long-term effects. A lot of the medication that we have that has been tried and tested, like aspirin, the aspirin has been around for so long, we're pretty sure we know the long-term side effects of it, right? And they're not that bad. But can you imagine a new pill? Yeah, you don't know what it's going to do to you in 10 years because you haven't been taking it for 10 years, right? And so they don't like a new pill unless it's proved to be effective and it does a better job. So if you're in the medical thing, you've probably seen this process. It may not have quite used the same terms, but does it seem a kind of natural way in which the medical world deals with proving something is effective compared to something else? So what I'm going to do now is go and look at our PowerPoint and see some of the questions or some of the topics that they have. And then after that, we'll go and we'll look at WebAssign and see what their questions look like. I think I had it up and I do. It's here. So here it goes. I'm hoping that this is the right one. Okay, here you can see the placebo effect. And one group receives it and the other doesn't. And when you group together your 200 people, one of the things you must make sure that you do is that you randomly assign each of your patients to either the control group or the experimental group. What you cannot do is take the ones that aren't that ill and give them the new drug, and the ones that are really, really ill, give them the old drug. Can you see how that would distort the results? So somebody who's in mild pain and severe pain, both kinds of people end up in both groups, and that keeps all the information balanced. And well, they just go through an example here. So here's a kind of horizontal version. So patient comes in with chest pain. You randomly assign them to group 1 and they get laser holes in the heart, and group 2 get no holes in their heart. So this is a kind of procedure rather than a pill. And then you compare the pain relief. Now, in a situation like this, you cannot have a placebo double-blind experiment. And the reason you can't is pretty obvious. You know if somebody shot a laser and made a hole in your heart because you had to go into surgery and get it done. And you know that they haven't put you into surgery in the second case, right? But there's no way of avoiding that. Can you see that double-blind is not going to work every time? You can't do it for surgical procedures, right? Suppose someone out there came up with a new way of doing a hip replacement, right? A new process, a new way of bolting it in or getting into the thing, whatever you want to call it, right? So they would have a random sample of 50 people who need hip replacements, and 25 would go and get the operation done the usual way, and 25 would get the new way of doing it. You made sure that the 50 people were random, right? Some are really old, you know, and have issues, and some are, you know, relatively young and quite healthy, and they're a good mixture. And then you do the treatment, and then you compare how effective that is. Now, the measures of effectiveness can be all sorts of measures. Couldn't it be time to recovery? Does it take you 4 months to get better, or does it take you 4 weeks? That's a big deal, isn't it, if you're old? You don't want stuck, you know, in the house in crutches for 4 months. 4 weeks would be better. Other effectiveness would be things that are a little bit harder to measure, but they can do it. Do you know that when you go to physiotherapy, they can do how much you can move, right? They can do the swivel thing, 10 degrees, 20 degrees, right? 15 degrees, 50 degrees. Those will also be recorded, and then they complete that, and then they can say, this new procedure does a better job, right? It's more effective at hip replacement than the old one. And then it gets repeated in Germany, and it gets repeated in Japan by other companies who do the same thing. And once everybody comes back and says, yes, we have duplicated what you found, right? What then happens is that pretty much everybody should take the new procedure and do it. So all the doctors who used to do it the old way, they basically go and get retrained. They go to doctors who knew the new method, right? They physically go and they train with them, right? They kind of, at the start, watch them, and then later on they help with it, and then at the end they do it themselves with the other guy watching. And once they're kind of trained up on the new method, they can then go back to their own hospital, and now they do that new procedure. So, you know, keyhole surgery was started by one person at one time, somewhere, right? And then they found how effective it was. And the data did that, and then it kind of grew into a population. So nowadays, very few people get their chest slit open and their thing opened up to get into your heart, right? They don't do it that anyway. You know how horrible the success rate when you had to do it that way? I don't even think they went through the front. Didn't they go through the back? Probably. Whatever. But now they do it with minute detail. They know that it's worked. That's what this is all about. Getting evidence that is replicable, right? I can do it in my hospital, and I can prove that it does a better job than the old way of doing the hip replacement, or the old way of replacing a valve, or whatever it might be. I'm going to share with you because I feel like it. Me and my wife were in Scotland, and we were driving around, and I noticed that my eyesight wasn't doing so well, and I thought it was just I needed new prescriptions. And so I went to the local ophthalmologist person, and they, luckily for me, they decided to give me one of those tests. I don't know if you've had one where they flash little lights and you're meant to hit a button if you see it. Field vision experiment, whatever it is. And I got one of them, and it didn't come out good. There was big chunks of my visual field that were dead, or weren't working. Let's say, not say dead. And she was very concerned. So she told me to come back the next day in case it was just a fluke. And I did the same experiment, the same test, and it came back essentially the same. And she told me, luckily I was going back a week later, that I needed to contact my doctor. And I went and I contacted my doctor, and I told him this field thing was coming up really bad, and the person in Scotland said I should see you right away. And it was great because I picked up the phone and he said, come and see me, you know, tomorrow. I'll get you in. I'll figure it away. And he did it, and it replicated. I had this, and it ended up, the bottom line is that I had a thing called a pituitary gland tumour, which your tumour's a little thing right inside your brain here, right? Sticks outside, a little curly thing. And the tumour was growing on it, and what was happening is it was getting so big, it was pushing on my optic nerve, and that's why I wasn't seeing so well. And so they went through the usual thing. I don't know if you get this. The first thing you do is you take a pill, because they found out that this pill, whatever it is very effective at reducing the tumour. It can basically just reduce it back to nothing, like shrivel it back up. But it doesn't work for everybody, and it didn't work for me. So what I then had to do after I went through that is I got that really cool surgery where they bore a hole in your nose and they bore a hole in your upper lip. And I was like, and they put these things in, and one of them's got a little camera and a lens on it, and the other's got this little gizmo thing, and it basically, it has a suction thing on it, and it chews up the tumor and it sucks it through the tube. I know it's disgusting, but it's fascinating to me, right? So if you're in the nursing program, this is fascinating, right? And they basically killed the tumor. They just destroyed it. They didn't do chemotherapy or anything, which would have been the next phase if that hadn't worked. Because chemotherapy and the brain don't play well together. So they took it out, and I'm being tumor-free. Really cool. I was lucky that they caught it the way they did. I was lucky that they caught it now. My surgeon was telling me that 20 years ago, it was a death sentence, because 20 years ago they didn't have the way that they do it. What they had to do is they cut your head off and they popped the top out, and they would try and get to the tumor, and the death rate was phenomenal. I mean, it was in the single digits, the number of people who lived after that. And I was just lucky to be born at the time and catch it at the time I got it. So I'm kind of lucky in lots of ways that happened. I was lucky it was in America, because I probably would have died if it was in Scotland. Because in Scotland, that type of surgery is hard to get, and you go on a waiting list. And I'm the wrong age. Young people get it done before old people. And I probably wouldn't have got on the list early enough to live. I would probably have died. So try and remember that the next time someone says to you that universal healthcare is a good idea, because you get what you don't pay for. So I'm against it. But, I'm a biased person, so that's okay. And we have drifted a lot because it's getting late, but I kind of just to, share things that are out there for us. And so let's look at some of the potential pitfalls. We've actually covered these, so I'm glad of that. There are a couple I haven't. So let's talk about these. Interviewer influence. So you're asking someone physically a question, person to person. And if you factor with the tone of your voice or your body language or whatever you do, you can actually influence someone's responses. So if you kind of do that shake the head that sometimes you do inadvertently, if you go and say, are you in favor of abortion? Do you see I'm already influencing you? And you might not even be picking it up. In fact, some of you right now are doing that. Do you know some of you nodded when I did that? Do you know what you're telling me? That you understood what I just said. See, I'm getting feedback. So I can give you feedback. So that is not good, right? And you would hope that wouldn't happen. But just the way that you say things, right? If you say it in a particular aggressive way or calm way or, authoritative way, you can make certain things, you can make certain people change or at least adapt their opinion. And voluntary response. It's not a good idea, for instance, to only let people who want to answer. To give you an example, see if you have OC and you have a place where you can go to tell people what you think of Olympic College. Right, how well we're doing as a job. Do you know that you tend to get people who go there? They tend to be people who had a bad experience. Complainers go to those sites a lot. If you had a really good experience, you might go, but maybe less so. And if you had, what you'd expect experience, you probably never go. So you see that if you only do people who voluntarily respond to it, you'll come up with the answer. 80% of OCU students think that Olympic College is doing a horrible job. Why is that? Because 80% of the people who went to that site said negative things about us. and only 20% said nice things about us. Do you see how that is a very big distortion? People who volunteer to answer questions tend to have strong opinions of them. That's why they're volunteering to answer, right? If you think, I don't care, you're probably not going to volunteer many times, right? And that is the end of that guy, at least what I want to do. I'm now going to, go and look at some of the questions on WebAssign. Okay, here are some. Overshot it by miles. 3, 2, 1, should be here. Okay. It says, the first one, consider a completely randomized experiment in which a control group is given a placebo for congestion relief and a treatment group is given a new drug for congestion relief. Describe a double-blind procedure for this experiment. Neither the patient nor those people administrating the treatment know who gets what. So that would basically be the third dot. That makes sense? You don't know what you're getting. The person, your doctor, typically doesn't know what you're getting. And that makes it. And they talk about why do you do this? The reason that you do it is it tends to eliminate bias. It tends to eliminate the placebo effect in particular. Question 2. Suppose that you're looking at the 2006 results of how the ECHO generating classified specified items as either luxuries or necessities. Well, that's a big term. Okay, in 2006, you said to people, do you think a car is a luxury or a necessity? Do you think eating out is a luxury or a necessity, right? Do you think having a widescreen TV, right? Those kind of questions. And people said yes or no, right? I can imagine that changed. Do you know in 1900, if you asked people, do you think having a car is a necessity or a luxury? Do you know in 1900, they would probably say it was a luxury. Now, I'm not sure about this one. What do you think about 1950? If you asked, do you think having a car is a necessity or a luxury in 1950? I know, could be a luxury still, right? Maybe. I bet if you asked people in the year 2000, wouldn't most people saying having a car is a necessity? You kind of need, most people, not everyone says yes to everything, right? But I would assume that into the year 2000, most people would say that that would be a necessity. So I'm assuming that this is what this echo generation thing is, that they ask people over the years the same things, and things move from necessity or move probably from luxury to necessities. And that tends to be a reflection of the wealth of a country. Do you know the wealthier you get, the more things you think are necessities? You know, if you're in a poor country, food is a necessity, right? Having a second home is not a necessity, right? But if you're very rich, you might start thinking, oh, well, I need, what do they call it, a summer home? Well, I need a summer home, right? That's a necessity now, whatever. Okay. Yes, people's ideas of luxuries or necessities rarely change. No, many luxury brands will no longer exist. Well, no, the generations 17, yes, it doesn't change much of the time. I'm not going to read through them. It's going to take me too long, but one of these is the right answer. Hopefully you'll pick the same one as the book does. Let's skip to one example here. Which technique for gathering data is a sample, an experiment, a simulation, or a census? So we've done some of these. Sampling, right? You get 100 people, right? An experiment is a bit more like the placebo thing. A simulation we haven't talked about, mostly because I don't ask you to do any questions on it. But if you're interested, a simulation would be where you don't ask anybody, you actually just use a computer to simulate something. You know, so like, Wow, that's a strange choice. An example of a simulation might be, do you know you can't crash cars into other cars very often because it's very expensive? Do you know a lot of the time they do simulations of that? They have a model of a car in a computer model, and then they crash it into things, and the computer model predicts what the likely event is. That would be an example of a simulation. And a census is you ask everybody. So here we go. An analysis of sample of 31 patients in New York hospitals suggests that poor and elderly sue for malpractice at 1/5 the rate of wealthier patients. Which technique for gathering data do you think was used? So they have a sample of 31,000. So I'm pretty sure it's not a census because that would have to be every single person. And I don't think that's all the people in New York. I know it's a big number, but it should be larger. It's not a simulation. There's nothing to do with computers there. It's either a sample or an experiment. Which do you think was used to get that data? Did they just randomly ask, 31,000 people? And from that, how many of you did you sue and how many didn't sue? Or did they say again?
I think it's sampling.
Yeah, I agree. So you might say, why isn't it an experiment? Well, can you see any reasonable way where you could split the group into old and young and they wouldn't know it? And then how would you do the double blind on it? I mean, it doesn't make sense. Do you agree that particular situation does not lend itself to doing a double blind experiment? And a lot of the time you pick up the trick after you've seen enough examples. It's a kind of experience thing. Oh, I remember a story like that before and that was a sample as well. Or I remember a situation like that and that ended up being an experiment, right? Or, oh yeah, if they ask everybody, it's a census. Don't even need to think about it, right? You start just picking up tricks like that.
Could we do another one of those?
Sure. I'm on calves. Let's do this one. Oh, is that the... Well, it's not really the same question. Do you want just a general question or another one about what kind of study is this?
Yeah, another one of the number 4s.
Okay. Oh, well,
like
we got them in
these
front of us. Let's do B. The effect of wind shear on aircraft, I think that's side winds that blow you off course, during landing and takeoff were studied by using complex computer program. I don't need to read the rest. Complex computer program. What was happening here?
Simulation.
Simulation, right? Yeah, don't overthink. Some of them are as obvious as they are, right? Let's do C. We're on a roll, we might as well. A study of all league football scores obtained through touchdowns and field goals was conducted. I don't need to read the rest. I already know what that is. And there's one word that gives it away. All.
If it's all.
And if it's all, it's a census, isn't it?
Census. Yeah.
Right? So sometimes it can be as simple as a single word, like computer or all, right? Cool. And why not finish the last one? An Australian study of 588 men and women who already had some precancerous skin lesions. Half got a skin treatment and sunscreen and sun protection factor of, wow, 17. And the other half got an inactive cream. After 7 months, those using sunscreen with sun protection had fewer skin lesions, right? What's going on here?
Experiment?
An experiment. They didn't do this. Is this a double-blind experiment? Do the people know what they're getting? And do the people who are measuring it know what they received? Well, I think if you look at this, these people are getting a skin cream with a factor 17, right? And the other people just got an inactive skin cream. Do you see that that is a placebo effect? You're getting a cream. You just don't know if it's good or not. And
Right.
we'll assume here that the doctors doesn't know which one you got. So when they come in and they get tested for how many skin lesions you've got, the guy just says patient A had 2, patient B had 5. and they don't know what treatment A or B got. So hidden inside that, I could make a reasonable assumption that not only is it an experiment, it's a double-blind experiment. Now, you can have single-blind experiments, and that's when only one of those two factors are there. You know, you could have a situation where your doctor knows what your treatment is, but you don't, right? You're just getting a pill, you don't know what it is, but your doctor does know that you're getting the good pill or you're getting the old pill, right? That would be considered a single blind, because only one half of the process is unknown, right? The person doesn't know what treatment they're getting, but the doctor does, right? That can sometimes happen, right? You could get it to, it's a little bit harder to do this, but can you imagine a situation where the person knew what kind of physiotherapy they were getting, right? They were getting the, you know, swim in the water a lot and do weights a lot, and the other person was bend a lot, right? Whatever, right? So they kind of knew what they were getting, but they didn't tell their doctor what they were getting, and their doctor was just testing their mobility. So you can see in that situation, the doctor didn't know and was told not to ask, right? The doctor who's checking what kind of treatment they were getting, right? What kind of physio they were getting. So the person might know, but the doctor doesn't. That's pretty rare, but it could happen, right? And the best version is obviously double blind, if you can do it. Right, as we went through those questions, do you see that just by picking up, oh, computer simulation, all census, you know, you've got a kind of idea of what's happening. How do I know this is an experiment rather than a sample? Well, in an experiment, don't you have two groups?
Mm-hmm.
At least two groups. In a sample, don't you basically just have a group of people and you ask them stuff? Now, they may be broken into groups, but that's not really part of the process. So that would be my main difference between the two. So I'm going to skip the CAV one, if you don't mind me doing that. Oh, actually, I can't skip all of them. So I'm going to have to do, okay, let's do this one. A skin patch contains a new drug to help you stop quitting. Help you. So, oh God, let's try that again. You can tell it's getting late. To try and get you to quit smoking. And a group of 75 cigarette smokers have volunteered as subjects to test that new skin patch. For 1 month, 40 of the volunteers received the skin patch with the new drug, and the other just got a skin patch with no drugs. And at the end of the 2 months, each subject is surveyed regarding his or her current smoking habits. So you got a patch, and then you went to your doctor or you went to the person who's collecting the data and they took it in. What was the question? Select all that apply. So there may be more than one box checked here.
Yeah.
Right, so they then record the smoking habits of all volunteers if different exists between the two groups. They then record the smoking habits of 40 volunteers. It seems if there's a difference between them. Okay. Use random selection to pick the 40 volunteers for each drug. You know, you would, if you're doing a good experiment, wouldn't you make it random? Yeah, you've got 80 smokers, but you don't want all the heavy smokers to get the patch and the ones that are light smokers not, right? That wouldn't really be a fair distribution, right? So you randomly select them. It says here no placebo is being used. Is that true? Remember, there was one group got a patch with a drug in it and the other group got a patch. It just didn't have anything in it. Isn't that a classic placebo preventing device? Isn't that what you do to stop the placebo effect happening? You don't know what you're getting, but you're getting something, right? So you wouldn't check off that one. What about this? Then record the smoking habits of done that. A placebo patch is used, so that one I would certainly put in because it was used. And this is going to be our last break. Some of the topics that chapter 2 deals with. Now, that first chapter could almost have been in an English class or a geography class or a social science class, right? There was no numbers worth talking about. You didn't do anything that you would consider mathematics. Wasn't it more reading and vocabulary and understanding how things were done? This chapter is a little bit different from that. You actually will get to deal with numbers, and you will actually get to deal with data that someone has already collected. So you're going to look at charts, how you can take data and summarize them with graphs and pictures. You're going to look at things like box plots, frequency distributions, and stem and leaves. So these are tables or visual pictures that take all that data and put them into some convenient summarized form so you can see the big picture. Right, so if I was collecting data on the ages of Olympic College students and I collected, say, 500 of you, it wouldn't be very helpful for me just to give you 12 pages with the ages of those 500. You see, it would make much more sense if I could put them into things like a histogram so you could visualize, oh, look how many 22-year-olds, I never realized there were that many. Or, we don't really have very many old students, right? We only have a couple of 60-year-olds and that's it, you know, whatever the information is. You see, if it's in a picture like that, you can actually get some good information out of it by just looking at what the picture is telling you. Trends and who's big and who's small and things like that. So that's kind of the gist of what's going on there. There is a PowerPoint one, but I'm going to just go and use my notes. And this is just a particular example of that type of picture data. So this is chapter 2, organizing data. That's hopefully what you're saying, right? And this is in Canvas. So this is a very interesting table. It's actually true data. It's not made up numbers. A lot of questions in textbooks just make up numbers, right? This is real data. If you're interested in the Titanic, this information is actually telling you who died and who lived in the Titanic. For instance, there were 325 people who were first-class passengers, and 203 of them actually survived the sinking of the Titanic, and 122 died. At the other side, there's 885 crew, and 212 of those survived the sinking of the Titanic, right? The one that was hit by the big iceberg. I can't remember what that movie is, but you know the movie where the guy holds the girl at the front, that one? I think it's called the Titanic now, right? That's the one they're talking about.
Yes, it's called the Titanic.
Right, good. So I couldn't remember it, even although it was in front of me, right?
My
So
goodness.
now, if you look at this data, yes, you can tell a lot more information the way it's written, right? You can certainly superficially, would you say, it looks like first-class people who had first-class tickets, survived at a greater rate than the crew. Does that seem reasonable? In fact, if you move to the second class, it's roughly 50-50. And then if you move to first class, it's not very good survival rate, and probably the crew is just equally as bad. So there's definitely some evidence there that first class and probably second class passengers survived at a much better rate than the crew or the third class passengers did. Now, if you put that data into form of what's called a bar chart, you can see first, second, third crew. If you put it into a relative frequency, basically that's just what percentage of them died. You can see this. And this is called the segmented bar graph. These are just showing you different pictures. This here is a pie chart of the count, and you can see this doesn't tell you about who lived or died. This just tells you the total number. So can you see in the Titanic, a large proportion of the people who were on the Titanic were crew. And quite a large group were third class, and first and second class were pretty similar in size. Now, here they're going through just all sorts of calculations that you could do on that data, but I'm not going to spend any great time on that, except to tell you one very interesting result. This is the percentage of people, right, in one group. Let's see if I can find a better version of that table. No, okay. If you look at the data, you find out, without argument, that first class people, a larger percentage of them survived than second class. Second class, a larger percentage of them survived than third class, and poor crew was last. And a lot of people put that information together and then they made the dreaded conclusion, which is where people tend to go wrong in statistics. It's not that the data tells you lies or tells you falsehoods. It's the people who look at that data, interpret it in a way that generates falsehoods. Politicians do that they call it the spin, right? They put a spin on the data. This is how you can look at this data, right? It's not that there are more people unemployed. The rate of increase in unemployment is now going down. What the heck does that mean? It means there's, it's not increasing at such a quick rate, but it's still increasing. So what people did there is one group of people said, see, that just proves what we already know. Rich people are selfish. They jumped on those boats right away and they saved themselves. And the poor third-class passengers, they never get a chance. That's why so many of them drowned. And the poor crew, they were busy trying to keep the ship afloat. That's why so many of them died. It's all to do with, society, right? Rich people are bad, poor people are good. I'm being really silly here, but that's the kind of argument that was done. Then someone else gave a different argument, which may be, that first argument, by the way, could be true. I'm not saying it's not. I don't think it is, but I'm not saying it's not. The second argument was actually quite subtle. Do you know that the data that you got was simply a factor of where you are on a ship when you had a first class ticket? First class ticket people were up high. In fact, most of them had doors right onto the deck where the boats that you would get into were. Do you know where third class people on cruise ships in those days were? Right under the boat. They had little portholes that you couldn't get out of. When a ship hits an iceberg and sinks really quickly, can you imagine how more difficult it is for those people to get out of their bed and get up to the top while there's a whole load of other people exactly trying to do the same thing? Crew, same problem. A lot of the crew did have to keep they were trying to, stop the floods, right? Keep the engines going, doing all sorts of things. They were, for the most part, they were doing that, right? So you can imagine why they were getting killed in such a high rate. Second class, not as bad. Second class weren't as low down. They still were quite high up, but it was only a couple of levels of stairs and then they were out on the boat. So you can see that the reason why the first and second class survived wasn't necessarily that they were rich. It was the rooms that they had were high up and therefore easier to get out of. Can you imagine a weird world where first class was right at the bottom of the ship? Your big rooms and you always were at the bottom, right? That's where first class, that's where they would have their cabins. Can you imagine a weird world where that would be true, right? Do you know in that Titanic, wouldn't all the poor folk live and the rich folk have died? It's a factor of where you are on your ship. So when they talk about data, it's the killer and the sting in the tail is two different people with different perspectives can look at the same data and come up with totally different reasons for why that's true. In fact, very often totally contradictory reasons why that is true. So statistician's job is not to do that. We're not meant to go into the data and say, now we'll tell you why. We'll give you the data and then you have to figure it out yourself. So let's look at this fella. Here's a whole load of numbers. It's the class of 30 students. That's called a frequency table. If I just gave you that big load of numbers, would you agree it'd be hard to tell anything? If I put it in, pardon me, if I put it into this table, can you see that only 2 of them got 8, 1 of them got 15, and it looks like the most popular score was what, 11? 8 of the people in the class got 11 in that quiz. Now, if you take that same information and you convert it into this fella here, which is called a histogram, can you see that visually it's the same information? But a lot of people, including me, because I'm a visual learner, can look at that and can see patterns of up and downness, right? See, it builds up and then it dies down. Right? Can you see that 11 was the most popular score, and if you read along, you can even tell it was 8 people. You see, that's a graphical version of this information in the frequency table. And this is the same information just written down as what we call raw data. See how helpful it is to put it in a table or a graph, a picture. Here is some data that's being converted into a frequency table, but this time the data is grouped. Rainfall from 0 to 1, 1 to 2, 4 to 5, 5 to 6. This kind of table is called a grouped frequency table. And the reason that they have to group it is, say if you just took the raw data and you gave one row to each possible number. So you can imagine 1.0, 1.1 inches of rain, 1.2, 1.3, 1.4. When you get a table like half the height of the house, with almost all of the numbers zeros, right? That table isn't worthwhile doing, right? Sometimes you have to group your data. So any rainfall between 0 and 1 inch gets counted together. Now you lose a little bit of information in this table. Do you know I can't tell now? Are these 5 people 0.1 inches? Are they 0.9 inches? Where they're a little bit this and a little bit that? That's lost. But at least I can now see a pattern. Can you see there's a kind of big and small? Can you see, for instance, that between 1 and 2 inches? There's an interesting little problem here. Do you notice that this group here starts with a 1 and this group here sort of ends in a 1 and the other one starts in a 1? What happens if there's 1.0 inches of rain? You can't double dip, right? You can't count them twice. That wouldn't be really accurate, right? So we have a rule, and it's a made-up rule, but you follow it. And the rule is, this doesn't mean 0 to 1. This means 0 up to, but not including 1. And this means 1 up to, but not including 2. That means if somebody comes and says 0.999 inches of rain, you're here. You see, you're still less than 1, so you still count. If you're 1.001 inch, you see you're here. And if you're 1 inch, you're still here. Now, this group frequency table gives you a different kind of bar graph. Now, do you notice that the way that you label the bottom is different? When it was individual numbers, you put the number right under each rectangle so everybody can see that's how many, that's 12 in the test, that's how many people. But when it's group data, do you see you go 0 to 1, 1 to 2, 2 to 3. So if I was looking at this rectangle here, do you see that would be the days of the week or the days of the year where there was between 3 and 4 inches of rain? You see how I could read that now? And it looks to me that this place has somewhere between, typically, about 1 to 2 inches of rain. That's what it looks like. Now, here is another kind of construction. It's called a dot plot. So basically, can you imagine that there's a ruler and you put in numbers at key points, and then each one of these dots represents a person. And this particular one asks people, what was the fastest ever speed that you've driven at? And they've given it in 2 groups. You've got men and women. So let's just use this as a comparison. If I look at this dot plot, it's called a dot plot because you use little dots, right? Pretty sensible name. I could say with a reasonable amount of confidence that guys typically tend to drive a lot faster than the women. If I just arbitrarily pick 110 miles an hour, which is ridiculous, but let's say it is 110. Can you see how many men there were that did that speed or more? And can you see that relatively fewer women? If you look at the women, in fact, the most likely fastest they've ever did was 85, because they're sensible and they don't break speed limits, right? Much. If you're looking at the guys, would you see that the data travels way over here before it kind of eventually drifts off? Isn't that more evidence that guys are dangerous when they drive? They drive faster. Do you know if you go for car insurance, they will take into account certain features of you, even though they don't know who you are, and they will decide what your insurance premium is going to be. So you could have 2 people with the exact same car going to the exact same insurance company and end up paying different insurance rates. Give you a good example. Some of you are probably in that right now. Do you know if you're less than 25, isn't your car insurance horrendous? Do you know why? It's not that they don't like you and they want to charge you more. Why are people less than 25 higher insurance rates?
Because they're reckless.
They have more accidents. They're reckless. And they collect data on it. Do you know what they do when they collect data on accidents? What age was the driver in the accident? That's one of the key numbers. And they've got years and years of data, and it just basically comes out that if you're less than, now you could be the safest 24-year-old in the world, and your brother's 26 and he's stupid. Do you know your brother's insurance rate will be better than yours? Because they do not take into account anything except age. Do you know guys get a worse rap than women? Guess why? We crash more than you do, right? Our insurance premiums are going to be more. So you could have a twin brother and sister with their own car, identical, yet he ends up paying more money than you do. It's all based on scientifically collected data. And it might seem unfair, but that's the way things work. They don't say, well, I know what you're like. There are some tweaks to that. Do you know in some insurance companies, if you've got a good GPA, they'll give you a reduction in your insurance? Now, they don't do that because they're nice or they're bad. They do that because, do you know, people with good GPAs tend to be safer drivers? That kind of makes sense. You know, if you, yeah,
More
kinda.
responsible.
More responsible, right? So that's how they collect this data. So that's what a dot plot looks like. Let's show you a couple more, guys, and then call it quits. This is an interesting set of data. It's called a stem and leaf. Here is the raw data, right? It's 30 pupils' test results, right? And the numbers go 35 up to about 83, as you can see. And the way they do this is you do a column, 30, 40, 50, 60, 70, 80, like this. And then 35 and 37. So do you see this number here, this 3 here? That doesn't actually mean 3. Do you know it means 63? So do you see you can actually still see the raw data, right? It's still there. You see it's kind of disguised in this stem and leaf. So the 8 means 80, 80 means 80, 81 means 81. So if I go up there, can you see the 80, the 81, the 81, and the 83? Can you see exactly where they are? Now, if you look at this stem and leaf diagram and you kind of turn your head on the side, don't you get a very primitive looking histogram? Can't you, for instance, tell that 60-something was the most common test mark? Right. 60-nothing, 61, 63, 69. 60-something was the most common. And wasn't 30-something the least common? And isn't there a kind of build up to the middle and then kind of drift away kind of thing? Now, when you create a stem and leaf, you have to give this thing here called the key. You have to tell people that 4/3, you pick an example, 4/3, anything will do, and you say that represents 43. For instance, do you know if I said 4/3 represented 430? So can you imagine you collected data and it was 410, 590, 620, right? Data that would look like that. Can you see that that 43 would now represent 430 and not represent 43? Do you know that this data could also represent 4.3, couldn't it? 4/3 would represent 4.3. So when you do a stem and leaf, if you do not give me the key, we can't look at those numbers and know what they are. Is that 5 there 35? Is it 350? Or is it a 3.5? You know, you can't tell. But if you give me the key, that you can. And the last one for today is a version of the stem and leaf called a back-to-back stem and leaf. So what we have here are the weights of 20 girls and the weights of 20 boys. And the stem goes 7 means 70, 8 means 80. So 12, 5, oops, I made an oopsie there. Do you know that should have said 12, 5 represents 125? Yeah, okay. So here is the distribution of the boys, here is the distribution of the girls. And when you look at this side-on-side thing, you can actually see a little bit of pattern going on. The most common thing that I'm seeing here is that there's not an awful lot of difference between the two groups, at least in this age group. Would you agree there's maybe a couple of heavier girls, but not that many? For the most part, aren't the patterns pretty similar looking? Maybe a little bit more flatter on this side than that side. So you can compare two groups quite easily. If you're going to do a dot plot, the best way to compare them is to make sure that the rulers that represent things are exactly above each other. So you can say that 90 is that 90 here, for instance. And that's going to be us for today. I think it's a good place for us to finish.